Now it's time for another Webinar Wednesday with TactoTek. Welcome on board. My name is Tua and I will be your host today. And our topic today is the IMSE design process. But before going into that, let's quickly go over a couple of practical things. Our webinar duration today will be approximately 30 minutes, which is then followed by the live Q&A. You can send your questions using the Q&A box in the bottom panel during any time of the presentation. And if you have other questions, please use the chat box for those. And you will have access to all presentation material as well as the recording of this presentation afterwards. So, what does it take to design a smart surface that combines electronic function, mechanical structure, and decoration in a single part? How do different engineering disciplines collaborate to create an elegant, effective solution? These and many other questions will today be answered by our very own Antti from TactoTek Product Management. Antti, please take it from here.
Yeah, let me start by sharing my screen. So let's get going. So as for the personal intros, keeping it short, like Tuva said, I'm Antti, Director of Product Management at TactoTek. You might see my face already in some of our previous sessions. In our series of webinars so far, we have covered many topics from the basics of IMSE technology to how we verify it, how we have taken into account sustainability, and we've also taken some deep dives into some of the engineering disciplines, just to mention a few. And like Tua said, today we will shed some more light onto IMSC part design and the engineering flow of it. And for that we're going to be I'm going to be doing that using our battery demonstrator as an example. In the battery project, we wanted to use IMSC in a use case demonstrator that was easy, especially for our automotive customers to identify with. So an overhead control panel was selected as the use case, since we thought that it would quite nicely bridge the gap between the traditional electromechanical parts and IMSC. Our intention was never to duplicate every overhead control feature and function that you would see out there in the market, but instead develop an IMSC application which would allow evaluating various HMI interactions in a familiar use cases added with the benefits that IMSC has over conventional technologies. So seamless, thin, and a lightweight 3D part. In addition, we wanted to use battery for validating IMSC structure against the relevant environmental and reliability requirements that an application such as an overhead console would need to comply with. So that was the starting point or the goal setting for the battery project. So like many of our or most of our customers or the customers of our IMSC licensees, we had to figure out and nail down the features and the functionality we needed for the product, and then figure out how the part should look like and behave. TactoTek, we are a technology company with strong R&D expertise, but we are not UX designers, nor do we have industrial designers in-house, like you may guess from this early sketch of what turned out to be a demonstrator that we are talking more about today. So partnering with an expert in this area was our way to go. And we asked a local award-winning industrial design partner to work with us on this project. We started by soaking our ID partner first with the basics of IMSC technology by explaining him the essentials of the technology, including the main differences between IMSC and conventional technologies, its benefits, the possibilities, and also the boundaries of the technology, and gave him intro to the basics of UI and HMI guidelines that IMSC introduces. So we basically use the elements from the content that we provide to our licensees in IMSC Designer licensing package. After this intensive induction, he started exploring how to get the most out of the seamless 3D part structure that IMSC enabled. The iteration sprint we did with a small team that involved the main engineering disciplines and the industrial designer. And actually part of that engineering team will be giving some insights to the project today. So only in few weeks we had concluded some low-cost usability tests and iterated the features, their locations, and overall the looks of the part. We played with different ideas for the passive haptic features and graphic variant possibilities we had in mind for the part. The important factors for keeping the cycle so short was, first of all, clear guidelines to follow, working as a one engineering team, and also efficient utilization of the design tools, CADs, and especially the simulators that work together like the engineers that are using them. We basically went around the first full cycle shown here. It's similar to what I guess could be called as a standard design cycle. So also an IMSC project starts with inputs, goes through a feedback loop of design and collaboration across many engineering disciplines. And throughout that feedback loop, each engineering role spits out different outputs at the different stages. In this process, we utilize the know-how and IP, what is nowadays the content of IMSC Designer, being the design guidelines and the instructions. Those are grouped in a way that TactoTek has found it's most efficient to execute IMSC project. So we had illumination and mechanics, electronics and antenna design and film and graphics engineers involved. Of course, it would have been even possible for one designer to take on other engineering tasks, but in our case, we had dedicated engineers for all of them. As said, the key was seamless collaboration between these engineers. For one engineer's change will ripple usually through each area. As an example, during this initial iteration round, there was constant like brainstorming going on between the illumination features, hardware and mechanics, and also the antenna was trying to reserve enough space for the radiator at the same time. But as said, working as one team, it was still painless to meet the design intent and to accommodate the needs of different engineering disciplines in a virtual space without having to produce one single physical part. When we were happy with the battery industrial design, the features and their functionality, the same process was basically repeated, only this time with more details and more accuracy, really going to the finest detail. So, like explained, since battery was created from nothing, we began with the industrial design, intended user experience, and other relevant requirements based on which we created the ID and the list of criteria and inputs for the functionality and also the performance of our part during that aforementioned first iteration round. In that process we use in our project, we are using a combination of those traditional electronics and film insert design domains working parallel on the same part. We're just combining them in a bit different fashion and enforcing them to really work as one team instead of separate verticals. So in Battery, we started like in an IMSE project in general with the 3D model or surface from the idea, which gave the look and feel of the product and the locations for the features. Based on this input, the illumination engineer usually defines the number of LEDs and locations versus the use case need and the application requirements. The hardware engineer designs the electrical layout, connecting and powering all the functions, keeping in mind the mechanical and material dependencies of IMSE. The antenna engineer designs the radiation pattern and location in sync with mechanics and tooling features to meet the transmission range and frequency requirements. And the software engineer works together with hardware and illumination, defining the LED driving, touch sensing, and so forth. So no job can really be done independently. There's sharing of decisions, models, drawings, and information at every step of the way. And it's important to know that although we have illustrated this as a linear path in this diagram, the project really makes the engineer sharing their outputs and details with all the other engineering departments at the same time as they complete their tasks. So after the mechanics designer creates the preliminary model, they will share their model and drawings with all the departments for them to begin their work. For instance, we will see the tooling designers to ensure the IMSE part is manufacturable and create the necessary tools for production. After any revisions to the part design, the model will be passed along to the illumination team to add the icon, select the LEDs and place them throughout the model. The new updated model is then shared with the hardware team to add the tracing layout with proper power being provided to each of the LEDs. If there are any antenna requirements like we did in Battery, the antenna designer will also reserve the space for the antenna and collaborate with the hardware team to ensure it has the proper tracing as well. And all this information is shared back again with the mechanics and every other department. Adjustments are made by each engineering department constantly to accommodate each other's needs in the product. The final output from each team will be the film and resin materials and thicknesses from mechanics as an example, as well as production drawings and models. From illumination, it's LED positions and specification, what types of reflective inks to use and lighting simulation results. From hardware, it's the 2D electrical layout, conductive inks that would be required in that application or part, the external control board design, from antenna specifications and so on. So constant communication is essential in order to ensure all the responsibilities and tasks are really being handled. Doing the design and engineering work like this, only within 1 quarter we had started from scratch and were already waiting for the tooling to arrive for the first production runs of Battery, which turned out to be a really cool demo that passed the automotive validations, and a demo which you might have seen live or hopefully at least in our digital content. Those of you who are not familiar with the battery, a quick summary of the features it contains. The battery incorporates capacitive touch buttons, a slider, illuminated icons, illuminated text, decorative light stripes, task lighting, hidden until lit icons. A Bluetooth antenna, obviously all this in 3D shape with different surface finishes and passive haptics. We did a short interview for a few of our engineering team members to illustrate with few concrete examples to kind of cross-functional design decision-making that I previously explained in a general level. And it's actually the team that's been responsible for producing the design instructions for the IMSE Designer and who are also behind the training modules we provide to our design license customers. So they truly know what they're talking about. So Tua, I think you're the best one to show us the interview and then take it from here.
First.
Okay, thank you. My name is Pasi Korhonen. I'm a principal engineer of illumination in TactoTek.
Yeah, my name's David Gregg. I'm a mechanics engineer at TactoTek, working on a whole bunch of different research and developments here and customer projects at the same time.
Okay, hello everyone. My name is Tuomas Heikkilä and I'm principal electronics engineer.
Thank you, gentlemen. And now let's go in the discussion. So do you have any good examples you could give us from the battery design process that would give our audience an idea of how you collaborated with each other during the detailed design phase of the battery, or where one change might have caused a chain reaction in the rest of the team, and what happened in practice?
Okay, so maybe I have the example of the Lifeline Illumination. So first of all, we made the illumination simulations for the Lifeline itself. And then as there's a courtesy light area very close to the Lifeline, we had the light leakage issue then. And based on the simulation, we made the rotation of the LED. So maybe we can discuss about that.
Okay.
Okay, I have a file to be shared. So here we have the simulation result of the Lifeline, what is presented here, fully illuminated. And then we notice that we have the hotspot on the courtesy illumination area here. And we notice that there is a LED that is creating the hotspot that is actually providing light to this Lifeline. So the LED is presented here. So we made a rotation for this LED so that this LED is contributing light towards this area and leaving the courtesy light away. And based on that simulation, we made a hardware layout change with Tuomas so that we can actually realize this change also in the product. So Tuomas, do you remember how did it go? What kind of work you had to do for that?
Yes, I can show it from my screen. Okay, so from layout point of view, of course, we placed our LEDs according to Pasi simulations, so we rotated all LEDs like Pasi has given our guidelines. But in addition to this, because we have so many LEDs needed for this light stripe and also in whole product, we should be able to drive enough current for each LED. And because of that, we need a bit, or we need to widen our main anode traces in the way that they are capable to drive enough current for each LED. And we can do this in the way that we increase the trace width, but more efficiently we can do it in the way that we add several narrower traces in parallel. And by that way, we increase the width of the trace, which means that the cross-sectional profile of our traces is bigger, and those traces can carry more current. And this ensures that the LED voltages are enough high for each anode. So basically, that's the main points regarding the LED and layout design in that specific area.
Since the LED requires a flat area below the LED, so the SMD quality would be good. So we made changes also to the B-film design, so that the flat area also covers the rotation place.
Right. There is a minimum requirement for flat area for LEDs, and when you rotate it, it kind of went into this 3D geometry area. So we needed to kind of adjust that on the mechanics side as well. I might have something to share, just give a better visualization of that. All right, you can see my screen, right? Mm-hmm. Okay, so this, I guess, is the area that everyone's sort of indicating down here. The LED, if you see my mouse, was rotated, and that was moving into this sort of 3D shaped area that we need to flatten out. So if we kept it as the regular 3D shape, when we actually mount this LED onto the film, it's not going to adhere properly. It needs to have complete flat surface, or else it can pop right off during thermal forming. But we can come right in here, let me move the resin here, and make that nice and flat just in this one localized area, while keeping everything else exactly how it was, the resin unchanged. And that way we can now make that simple change that Posse wanted, to have the light leakage kind of fixed in that area. It's such a small change, but it really takes everyone to really talk and communicate to this detailed level in order to make sure that everything can fit just fine, and we don't have any interferences or anything. Like, it even comes down to like the simplest screw tower. Like Tuomas was just mentioning about the traces and the width around them having to be increased to account for the current. And when traces are changed, we have to make sure they don't interfere with any of the screw tower positions. So we have our fixing locations, and just coming close to there, we need to have that clearance between everything, because during production, we're going to have all these traces move and shift with all the forming and injection molding. And we got to make sure that none of them really fall into these fixing features. So even if Tuomas wants to make a new tracing proposal, or if I want to move one of these towers slightly, we need to actually mention it and re-share our layouts with each other to make sure that nothing is interfering with each other. So it really is a constant sharing and communication between everyone to make sure that we all know what's going on, and we're not stepping on each other's toes. So
yeah, exactly. Is there anything else coming to mind about what kind of issues or features you have to take into consideration?
Maybe one thing about the antenna placement in battery. So it had to be a certain area in order to work properly. So I have an example here about the battery with clear A-beam. I hope you can see that. So the antenna placement is right here. I hope you can see it's a bit shiny, but there's an antenna here which is having a shape on B-film, and the shape typically in B-film creates different kind of reflection for the illumination. And since we don't have any similar shape here on the different side of the product, so we have to do something that we don't see any illumination defects on this side, and it's looking different. So the way we did was that we had A-film printing, and we were having it white, and this has to be translucent since we want the courtesy light out here, and the translucency of the area has to be as high as possible since we want all the illumination performance out of that product. So we need to mix a certain ink set so that this is hiding all the features of B-film and not showing any illumination defects because of the antenna. And then we ensured also that we get the maximum light output from the part. And we managed to create an ink concentration that fulfills those both criteria.
Thank you, David, Pasi, and Thomas, for this very interesting discussion. And now let's get back to wrapping up the webinar.
So obviously, it's difficult to give an all-inclusive example with details in such a short time, but I think those gave some kind of idea how an IMSE engineering team works together and how the design decisions made by one engineer impacts the other areas. In case you're interested in finding out more about the IMSE design rules, the methods and ways of working, don't hesitate to contact us, because we are really here to help you all the way so that you can start making your own IMSE designs. Our IMSE Designer licensing package will give you the needed design guides for all those design disciplines of IMSE that were discussed in this session. We have also worked together with our design tool partners to embed some of those IMSE rules into the CAD systems to ease your design work. As part of the licensing content, we also provide numerical design data for different material stacks and give also some reference designs for the functionalities that are enabled by IMSE. And instead of just giving an access to the theory and data sheets, we also have self-paced pre-recorded training modules, which will guide you through the foundational IMSE guidelines, the best practices with case examples to show what's really needed to transform your products into cutting-edge IMSE technology. But I think that's all for today. So if you have any questions, now would be a great time to hear those.